Hey guys, so today we are going to be talking about something called sequences. And our focus today is writing the equation for these sequences. And we have two ways to do that. So we have recursive and explicit formulas. Alright, so sequences. So you're familiar with sequences and what they are. I'm going to give you a formal definition here in a minute. But here's just some examples of sequences. So we've got 1, 3, 5, 7, 9. So those are odd numbers. If you're going from term to term, we go up by 2. The individual items are called terms, by the way. This next one, we go 5, then 10, then 20, then 40. So obviously we are multiplying to get from term to term here. This one, 1, 2, 1, 2, 1, 2, 1, 2. Pattern's pretty clear here. 1, 4, 9, 16, 25. So those are perfect squares. So here you're not multiplying or adding to get from term to term, but there's a definite pattern there. Alright, so let's talk about the formal definition of a sequence. So a sequence is a function whose domain is the set of natural numbers. So natural numbers are just 1, 2, 3, 4, and so on. The terms, like I said, are the range of the sequence. So you sometimes may not actually see the domain, but the range is what you're actually looking at. Okay, so the domain is the set of natural numbers. So we use n. It doesn't always have to be n, but n is a common variable. So the domain is always going to be 1, 2, 3, 4, and so on down to what we will call the nth term. Okay, the symbol for each individual term, again, usually but not always, a sub something, so a sub 1, a sub 2, a sub 3, a sub 4, on down to a sub n. And I'm just going to pick an example sequence, and I'm just going to do the first one I showed. So 1, 3, 5, 7, on down to the formula for the nth term. So in this case, that would be 2n minus 1, because if I wanted to get even numbers, I'd have 2n, and then this is just 1 less than that. So now we're going to talk about writing a formula for the sequence. So there's going to be 2 of these. The first, what we're going to talk about, is called a recursive formula. So a recursive formula is a formula for finding the terms of a sequence using 1 or more, depending on the sequence, of the previous terms. Okay, so let's look at our, use a different color. 1, 3, 5, 7 sequence. Okay, so here, the really nice thing about recursive formulas is they're very easy to write if you can see the pattern. So here our pattern is to add 2. And that's what a recursive formula does. So in a recursive formula, you are essentially going to say, to get the next term, add 2. But if we're going to add 2, we need to know what we are adding to. So we always have to start with an initial point. So we always have to define what A1 is. So in this case, A1 is 1. Now, the recursive formula is going to say, how do I get to the next term? So how do I get to the next term, or in this case, the nth plus 1 term? Well, we are going to take the previous term, which if this is a n plus 1, the previous term would be a n, and we are going to add 2 to that. So there's a lot of notation here. So you always have to define the first term, and then you're going to define how are we getting to the next term. So in this case, I am adding 2. Now, you can write this in different ways. So I will always, just out of convention or habit or just a decision, use the nth plus 1 term, but as long as the subscripts follow, you can write it in different ways. So I could also say a1 is 1, and to get to an, I'm taking the term before it, which would be an minus 1, and adding 2 to that. So these two things are saying the same thing, that if I want a4, then I need a3, and I'm going to add 2 to that. Okay, so let's do another example. Let's do our 5, 10, 20, 40, and so on. So again, the pattern here is clear. We are multiplying by 2, and in the recursive formula, that's exactly what we say. So I'm going to say a1 is 5, and to get to the next term, an plus 1, I'm going to take the previous term and multiply it by 2. So I'm going to say 2 times an. Okay, so, and you can write that in slightly different ways, but it's how are you getting to the next term. The nice thing about recursive is, like I said, it's if you see the pattern, all you're doing is writing the pattern. The downside is if I wanted the 50th term of this sequence, I need to know the 49th in order to do so. So there's some drawbacks there. I'm going to give you one more example of a recursive on a very famous recursive sequence. So sequences can come in many forms. You can add to get to the next term. You can multiply to get to the next term. This one's a little bit different. Okay, so some of you have seen this before. This might be new to some of you. This is what is called the Fibonacci sequence. Sequence. So Fibonacci's the guy, he did a lot of stuff in math, but this famous sequence is called the Fibonacci sequence. So as you have been looking at it, hopefully you have seen the pattern. And the pattern is to get to the next term, you're adding the 2 terms before it. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 5 plus 8 is 13, and so on. So here we can write this recursively. And this is a sequence that really, you can only write it recursively. So A1 is 1, but that's not enough information for me to get to the next term. So in this case, I actually have to define both of the first 2 terms. So A1 is 1, and A2 is 1. Now, to get to the, and again, the subscripts here can vary, but I'm just going to stick with my an plus 1. To get to the nth plus 1 term, I'm going to add the term before that, which would be an, and the term before that, which would be an minus 1. So there's, again, the subscripts, as long as they match, all of them are valid. So that is a recursive formula. All right, so continuing with sequences, the second way we have to write an equation for a sequence is what's called an explicit formula. So an explicit formula is a formula for finding the terms of a sequence using the term number, meaning if I want the 100th term, I can plug in the number 100 and get out that value. The advantage is obviously in a recursive, if I wanted the 100th, I would need the 99th term. But in an explicit, all I need to know is the formula and what term I'm trying to find. So the downside is they are harder to come up with. So let's look at our 1, 3, 5, 7, and so on. Okay, so one strategy that I suggest is lining up the term number next to the term. So 1 is the first term, 3 is the second term, 5 is the third term, 7 is the fourth term. Now this particular sequence is a special type of sequence that we will talk about later on in the course. But for right now, we're just going to look for the pattern. And we've already established we're going up by 2. But now what we're looking for is how do I plug in a 1 and get a 1, plug in 2 to get 3, plug in 3 to get 5, plug in 4 to get 7, and so on. Okay, well, I look at these numbers, and if they're going up by 2, so there's something there. If I double 4, I get 8. If I double 3, I get 6. If I double 2, I get 4. So these numbers are 1 less than double the term number. So my nth term, okay, in terms of n, so these are all n, is going to be 2 times the term number n minus 1, because 2 times 1 minus 1 is 1, 2 times 2 minus 1 is 3, and so on. Okay? Alright, so given a sequence. So my sequence here is 2, 4, 8, 16. We want to write the recursive and explicit formulas for this. Okay, so let's start with recursive, because recursive, like I said earlier, is much easier to come up with. Okay, so recursive, we're always starting with our first term, always have to define what A1 is. Then we're looking at how are you getting to the next term. So here we're going from 2 to 4, 4 to 8, 8 to 16, and hopefully you see the pattern that says I am multiplying by 2. So my an plus 1, my next term, is 2 times the previous term. Okay, explicit is a little bit trickier. Again, this particular sequence will have a special name coming up, and we will have a formula for writing the explicit formula, but for right now we can just kind of do some trial and error. So again, this is 1, 2, 3, 4. So I want to be able to plug in 1 and get 2, plug in 2 to get 4, plug in 3 to get 8, and plug in 4 to get 16. Okay, well you might say, well, just multiply by 2, because 2 times 1 is 2, 2 times 2 is 4, but 2 times 3 is not 8. So that is not the pattern. But what we're doing is we are multiplying by 2. So I have 2, 2 times 2, 2 times 2 times 2, 2 times 2 times 2 times 2. So my explicit here is going to be 2 raised to the nth power. Alright, now what we're going to do is write out the terms given a sequence. So my first sequence, A1 equals 7, AN plus 1 equals AN minus 3. Alright, so we want the first 5 terms. And you'll start to see the pattern pretty quick here, but I'm going to kind of go through this slowly just so we see the subscripts and how all that works. So the first 5 terms will be A1 through A5. So A1 is 7. A2 is going to equal, if this is 2, that means A1 is going to be A1 minus 3, which means 7 minus 3, which means 4. Okay, A3 is going to equal the term before it, A2 minus 3, which means 4 minus 3, which gives me 1. A4 is going to equal A3 minus 3, which is 1 minus 3, which is a negative 2, which makes A5 equal to A4 minus 3, which is negative 2 minus 3, which is negative 5. So this sequence is 7, 4, 1, negative 2, negative 5, and so on. But those would be the first 5 terms. All right, next one. I still want the same 5 terms. Okay, but this time instead of being a n and a n plus 1 in the equation, we have n. So this would be an example of an explicit formula. So to get a 1, we will plug in 1 for n. So that's going to be 4 times 1 minus 1, which will be 3. A2 will be 4 times 2 minus 1. 8 minus 1 gives me 7. A3 is going to be 4 times 3 minus 1. A4 is 4 times 4 minus 1. And A5 is equal to 4 times 5 minus 1, which is 20 minus 1, which is 19. So here, rather than using the previous term, you are using the term number 1, 2, 3, 4, 5 versus the previous one where we used the previous term to generate it. All right, our last example here is a little bit different. This is not as commonly seen. So by far, just a straight explicit and recursive formula is what we're interested in. This one's sort of a combination because we have both n and an in here. Okay, so we're going to pay special attention to the subscripts here, specifically the n on this side of the equation. So a1 is defined as just 2, so we're good there. Okay, A2, okay, looking at the subscript on this side is n plus 1. So this is a little bit weird because that means A2 in this format is A1 plus 1, making n 1, which means this is 1. Let me go down. That means we're looking at 1 times A1, which is 1 times 2, which is 2. So let's keep going. A3, written as a number plus 1, would be 2 plus 1, which means my n is actually 2. So we're going to have 2 times A2, which is going to be 2 times 2, which is 4. Okay, and again, this is beyond a typical problem. So A4 is going to be A3 plus 1, which means our n is 3, which means on this side of the equation, we have 3 times A3, which is 3 times 4, which is 12. Our last one, A5. I apologize about the shadows, working on it. Is going to be A4 plus 1, which is 4 times A4, which is 4 times 12, which is 48. So just paying attention to the subscript and how that's written, this sequence then would be 2, 2, 4, 12, 48.